Okay, so this one's similar to question one. It's just saying that they want you to find the non-permissible values. So what you need to look at is any denominators and anything that could create a denominator for question 1a. So in this case, we have 1 plus sine theta in the denominator. So we know that it's not allowed to be equal to 0. And then we have 1 plus sine theta, which also can equal 0. And then you also, this is kind of the trick, is if you ever see tan or these reciprocal kind of relationships, you need to write them as what they are, as a reciprocal, so that you can see what's at the bottom. So in this case, this is the same as writing 2 over cos squared theta, which means that cos squared theta is in the denominator, which means that that cannot be equal to 0 as well, right? So anything in your denominator. So then you just solve for each of these and solve for any angles that will give you these values. And we always try to, with trig, we always try to summarize and simplify everything and put it together. So sine theta is not allowed to be equal to -1 when you bring that 1 over. And then sine theta is not allowed to be equal to, oh, in this one, it should be, when I bring it over, it should be -1. Oh, I think I'm missing something. Oh yeah, there you go. That's what I'm missing. Just looking at that. Okay, so this one's -1. This one is where 1 cannot equal sine theta. So it's +1. And the last one, you would just square root both sides to give you that cos squared, or cos theta is not allowed to be 0. So for these, whenever I see the values, the answer is being 0, 1, or -1, I always use the quadrantal angles. I always kind of draw this at the side, and then I look at where the angles are becoming either -1 or +1. So these are the quadrantal angles on the unit circle. Okay, there you go. So with these angles, so we're looking at where, in this case, it's always the sine is always your y coordinate and cos is always your x coordinate when we're looking at these unit circle values. So we're looking at when the y coordinate is -1, and that occurs at 3 pi over 2. Okay, so 3 pi over 2 is the equivalent to 270 degrees. Okay, so that would be the angle that it occurs for the first answer. Okay, so that's the first one. So that's only looking from 0 to 2 pi, meaning 0 to 360 degrees. The next one, we're looking at where the y coordinate is 1. The y coordinate is 1 at pi over 2, which is 90 degrees. So that's going to be equal to pi over 2. And the last one, we're looking at where the x coordinate is 0. So that occurs at pi over 2 and at 3 pi over 2. Remember, pi over 2, 90, 3 pi over 2 is 270. So now we just have to summarize this, okay? So we can summarize this by saying that I know that there's going to be an answer here and here. So we can actually write this as one general solution. So the general solution to this is where I say that pi over 2, which is my first answer, plus, to get to the second answer, I would have to add, that would be equivalent to 180 degrees, which is pi in radians. So if we add pi, that's going to take us to 3 pi over 2. And then what we need to say is, well, what if I go multiple times around the circle? Well, if I add another pi, that takes me back to that pi over 2 position. And if I add another pi, that takes me to 3 pi over 2. So what I want to say is that if you're adding numbers of pi, so pi n, where n is an integer, because you can go in the positive direction or the negative direction, as if you keep doing that, it's going to give you every answer around this entire circle if you go multiple times around. So this is when they don't give you a domain, like in A, they're kind of looking for the general solution. Sometimes you can summarize it to be a single statement, or sometimes if it doesn't work out, you might have to do multiple kind of statements like this, and then the next one could have been like 3 pi over 5 plus 2 pi n, where n is an element of real numbers. So usually this is what we use, but if we can if we can make it represent all the answers, we try to. So it's just about writing less when it comes to these trig kind of general solutions. Does that make sense, Sarah?
Yeah.
Okay. Okay, so that's question one, is just finding your non-permissible values. Don't forget to write the reciprocal relationships, and then just looking at what values could make that happen. That's it. Okay, so there's usually going to be more than one answer when it comes to like the non-permissible values. So this one's asking for in radians. B, verifying. This is where you can just do this. You can just do this either graphically, or you can substitute these values and just see that the left side of the equation equals the right side. So all you're doing is you're going back to the original question, and in your calculator, you would substitute using radians mode in this one. Theta would be replaced with 7 pi over 3. And then to put secant squared theta in your calculator, you would have to go 2 divided by cos, and then you'd go 7 pi over 3, and then you'd square this answer, okay? So if you put this into your calculator, you should have gotten that the left side is 8 and the right side is 8. So as long as you can kind of type it into your calculator, that's the only issue. So things that you can do to kind of make it go properly is just making sure there's brackets in your denominators here in this case, right? So all this stuff will have brackets to make sure that they're properly being divided. And then for the next one, you would have to be in degree mode. And you would do the exact same thing, but as long as you're in degree mode, you'd be putting the theta as 120 degrees. So you just have to switch modes when it comes to getting the right answer. And then just watching your brackets. And then just squaring outside the brackets, okay? So that's pretty much, you're just seeing what is the left side equal to, that's what you'd write down, and what did your right side equal to, and what you should be showing me is that the left side equals the right side. You'd say left side equals right side, and that's how you're verifying. You could also graph this, and if you graphed it, you could then go trace 7 pi over 3, and then see if on both equations they give you the same y coordinates, right? So that would be your verifying process. One node, other node. Just make sure that kind of switches between them. How's that sound? Good?
Yeah.
Sarah, do you mind muting your mic and then just come on anytime, just because there's like a little feedback coming on. Thank you. Perfect. Okay. So the next one is just proving the identity. Now there's rules, and this is what, it's kind of like a game, I find. Like these are my favorite things when it comes to this course, is just proving, because all you're doing is playing with it like a puzzle until it looks like the other side. So there's things that you want to look for is, first of all, if you see anything with tan or cosecant or those reciprocal relationships, you need to write them as either sine or cos. So I'll always try to get everything to look like sine or cos. And then one of the most common things that you'll see is that the Pythagorean identity, where it's like sine squared theta plus cos squared theta equals 1, right? So that would be something that you can use just by rearranging the equation. If you ever see fractions, get common denominator. So it's these like general rules that you want to follow. And if you follow them, you'll see that it should work out in your favor. Okay, so I'll show you these. And then I find it just comes with practice that you'll start to see like the patterns, and then it becomes just like a fun puzzle. So usually people don't like it, but if you work on it, it's kind of like the best thing. So if you're a puzzles fan, this is for you. So I always work with the most challenging side first. So I'll start with the left side. So in this case, 1 plus sine theta and 1 minus sine theta, you can't really do anything with them. You can't, those are not the Pythagorean theorem identities, because you would have to have the sine being squared. So that's not something I can do. So the only thing I can really do on the left side is get common denominator. So that's usually what I try to do for examples like this. So that's a factor. And then the left side, the other one, the other fraction, that's the other factor. So I need to multiply both sides by each other's factor. So I'm going to multiply the first fraction by 1 minus sine theta and the top by 1 minus sine theta. And then the right fraction, I'm going to multiply by 1 plus sine theta and top as well. And then I just continue on. So at the top, 1 times that factor doesn't change it. Plus, when I multiply those, that doesn't change it as well. The plus sign here doesn't need to be distributed because it doesn't change the value. So that's the top. The numerator looks like that. The bottom, I'm going to write it as a single denominator. So common denominators equals one common denominator. And then at the bottom, I'm actually going to FOIL that out. So if you ever see that they're conjugate factors, then you do want to actually put them together. And then what you'll also notice at the top is that we have sine theta minus, so minus sine theta plus sine theta, those guys will cross each other off. And then 1 plus 1 is 2 at the top. At the bottom, once I do FOIL, it's going to be the first terms multiplied with the outside and inside terms canceling each other off when it comes to conjugate terms. And then these guys are just going to multiply to give us minus sine squared theta. And this is where I was saying that this guy right here is the Pythagorean identity. So whenever you see something with squared, like sine squared theta or cos squared theta with a 1, check that it's not this, because this is the Pythagorean identity. And if you rearrange this, you'll always be able to replace it. And that's one of the most common steps when it comes to proofs. So this proving will actually come back in calculus. So you'll see this proving thing come over again, and there's like a whole section on it. So if you focus on this, next year will be easier. So what you want to do is you want to solve for cos squared theta, which is equal to 1 minus sine squared theta. So as you can see, I rearranged the Pythagorean theorem, and I just realized that this can replace the whole denominator. So it's going to be 2 over cos squared theta. And if you look at the right side of the equation, we're almost there, because 1 over cos squared theta times 2 is the same as saying, I should put the 2 at the front just to make it a little bit better. 2 multiplied by 1 over cos squared theta is the same as saying 2, and that's secant squared theta. So this is that reciprocal relationship where that square just follows along. Okay, and as you can see, then you just say left side equals right side. And usually when it comes to proofs, you'll notice that once you get into the higher levels in university, they usually have this little box and they shade it in. And that kind of means that the proof is completed. So if you look at some of the advanced textbooks, if you ever looked at it, there's this little box at the end showing that you're done. Okay, so that's just, you don't have to include that now. It's just if you do see that in the future, that's kind of what it means. So that is the proof. As you can see, once you get the right side, you're done. Now, if you get to a certain point and you've simplified the left side or the right side as much as possible and it doesn't look like the right, then you can maybe switch to the right, but you don't really want to jump around. You kind of want to work with one as much as possible. And then once you're done with a side, then go to the other side. If you're not done, if it hasn't done anything for you. So number 2, how are you doing with proofs? Sarah, how are you doing? You good? Okay. Are you finding the proofs are challenging, or how are you finding them right now?
They're okay.
Okay. It's like a puzzle,
Yeah.
Like, do you find that you're getting like, it starts to get too long or too crazy, and then you're like, where do I go from here?
Yeah, sometimes I get stuck, but then I just like erase it and restart it.
Yeah. You'll see once you start to see kind of like once you kind of go through the homework and you'll see the same thing come up, you start to kind of know what they're looking for or what you want to do to make it easier. Because there's so many ways, and there's not just one way. So if at the back it looks like they went one way and you went another way and still got the same answer, it's not wrong. It's just that there's like multiple ways of substituting.
Yeah.
Right? Okay, so number 2 now. So these one's in radians, one's in degrees. So let's do the degree one first. So you can choose. You just have to figure out two numbers, two degrees that either add to 165 or subtract 165. It doesn't matter what they do as long as they are numbers that you can get exact answers for. So like, so the ones that are most common are 30, 60, 90, using 180, using 120, 150, 270, 360. Those kind of numbers are what you kind of want to use when doing these questions. So for this one, I chose where tan 165 could add up to 120 plus 45 degrees. So whatever method you chose, as long as it adds up to the number or subtracts to that number, you'll still get the right answer. And then you want to look at your formula sheet. Your formula sheet, especially for proving and this stuff, helps a lot because you just want to see something that you can replace it with. So we're going to use the identity for tan when you add A plus B. So that's going to be where you have tan A, this is A, and this is B. Now you can switch them. You could have A being 45 and then B being 120. Wouldn't make a difference. So it's going to be tan of A plus tan of B. Just looking at my formula sheet. Over, it's 1 minus tan of A multiplied by tan of B. And then what you do is you want to replace them with what they're equal to. So this is where you either draw that special triangle. I usually try to draw and figure out what quadrant it's in because that will tell me using the cast rule if it's a negative answer or a positive answer, right? So 120 is in the second quadrant and 45 would be in the first quadrant. So for 120, we know that the reference angle would be 60 degrees. And for 45, that is the reference, right? So you don't have to really work on that one. And then once we have a 60-degree angle, remember you need to write out what values you have. Now, there's lots of options. Like I find it's up to you kind of what you want to do. If you want to look at the unit circle now, or you want to kind of, if the 20-1 stuff is very strong with you, then you can use just that special triangle where 30 is opposite to 1. Your hypotenuse should be 2, and then opposite to 60 should be root 3. Okay, and then for the 45, it should be opposite and adjacent are 1, and the square root or the hypotenuse should be square root of 2, right? So you could rationalize these right away and write them as fractions. Like there are so many ways to do this unit. And that's what I find is really challenging with this unit is that it's just like one method is easier for one question versus another one for another question. So that's why it's like in the past, I used to teach it where I used to teach it only in degrees, and then every single answer we would just convert. But it's nice to build kind of an understanding of what radians are and use those as well. So it's kind of been like a work in progress to see what works for students and what doesn't. So tan 120 is in the second quadrant, which means that it's going to be a negative answer of tan of 60, because that's the reference angle that we're using for the ratio. It still means the same thing. So tan of 60 is opposite over adjacent, which is root 3. So it's going to be negative root 3 for tan 120 degrees. Plus tan of 45 degrees is opposite over adjacent of 45, which is just positive 1. So that's the top of your fraction. The bottom, you're going to have 1 minus, same values, because it's still tan of 120. So in brackets, I'm going to put I want to put negative, root 3. And then tan 45, 1. So I'm just replacing them with all their answers. At the top, I'm going to leave it the same. At the bottom, I'm going to rewrite it as 1 plus because the two negatives become positive, and then square root of 3. So the only thing you have to do here from this step is even though the textbook doesn't really do it, I find that it gives you kind of like this answer sometimes. It is still important to rationalize. So I'm going to multiply the top and bottom by its conjugate. And then I would do FOIL for the top, and I would get negative root 3. And then I would get positive 3. Oops, why didn't that go? Positive 3. And then I have plus 1. And then minus root 3. So that's FOIL over, whenever we do FOIL of its conjugate, it's just going to be the first terms technically multiplied and then your last terms multiplied. So we can summarize it to just be 1 minus 3 at the bottom to save yourself some time. And then we're going to have 4 minus 2 root 3 over negative 2. And the only thing I like to do is I want to divide all the coefficients by negative 2. So that's going to be negative 2 plus root 3 as the final answer. Okay. So you can confirm your answer. So when you do this question for yours in your assignment, put tan 165 in degree mode into your calculator, and it should give you the exact same decimal answer as negative 2 plus root 3. So that's how you know that you did it properly, is your answer should match what tan 165 is. Okay, so this is just that exact way of getting the answer, and it's just that process of using your special triangles. And then you kind of repeat this for the 7 pi over 12, but then you're just going to use radians mode, or you're going to just be in radians. So that's the only difference for that one. And then you need to use what sine A plus B is, or what sine A minus B is, depending on how you chose to do these. So don't think that there's just one way, there's multiple ways to get these answers. So we're doing sine 7 pi over 12. Okay, so you just have to figure out two kind of special angles that add up to that. And I chose to use sine, I think pi over 4 plus pi over 3. Yeah, because I would get common denominator of 12 and I would have 4 plus 3. Yeah. Okay, so these are the two I'm choosing, where this is A and this is B. And then I'm replacing it in that angle, that addition, that sum. It's called like the sum identity. So I'm going sine of A, which is pi over 4. And then we have cos of B, which is pi over 3, plus cos of A, pi over 4, and then sine of B, which is pi over 3. There you go. And again, use your special triangle. So at the side, I always kind of draw my special triangle. For this one, you're going to use pi over 3. Pi over 3 is 60 degrees, which is always opposite to root 3. Your hypotenuse is 2. And then opposite to pi over 6 is 1. So whenever I do the special triangles, I do like to have the radian values converted. So like, I mean the degrees written as radians, just so it's easier to kind of to see what they look like. And it gives me practice too, while it reminds my brain what everything is. Okay, so there's your special triangles redrawn for radians. So sine pi over 4, you're just looking at the opposite to the hypotenuse, which is 1 over square root of 2. Multiplied by cos pi over 3, which is your adjacent over your hypotenuse, so I have 1/2. Plus cos pi over 4 is adjacent over hypotenuse, same as sine pi over 4. They give you the same answers. And then sine pi over 3 is opposite over hypotenuse, so it's going to be root 3 over 2. So the nice thing is that once you actually multiply them, you'll get common denominators without having to do any effort here. And then the tops will add together to give you 1 plus root 3, and the bottoms will add to will just become a common denominator since they're already the same. So it'll just be 2 root 2. And then with this answer, just rationalize it. So since it's a monomial at the bottom, we're going to multiply the top by root 2 and the bottom by root 2. And so then we're going to distribute that square root of 2 into the top. So that's going to be square root of 2 plus square root of 6. And at the bottom, it will be 2 times 2, which is 4. Now this can't be simplified any further because you can't take out anything from 6 and 2 as radicand. So that is your answer there. Again, you can always, in radian mode, check if sine 7 pi over 12 is equal to this answer. And that's how you're like, yep, I can move on. So that is 2C. Let's go on to question 3. You okay, Sarah, so far? Okay. Okay, so this one is just proving again. So left side equals right side. So like I said, I always, in this case, I'm working with the left side, and then the right side doesn't look that simple either. So I would actually switch to that as well. So I did it 2 ways. It's funny because I did it first and I was like, oh my gosh, this is long. It was like 15 steps. And then I looked back and I tried it one more time, and then I got it down to like 4 steps. So there's always like a long way and then there's a short way, right? So again, you'll get it right. You'll just take longer, right? So it'll still be right if you take the 15-step way or the 4-step way, as long as you get the left side and the right side being the same. So I'll show you the simpler, faster way. So first of all, we have sine x plus, instead of tan x, I'm going to write it as sine x over cos x. So like I said, it's really important for these to have your formula sheet in front of you and look for what you can replace it with. There's Wilfred. Knew you'd come. Okay, so that is the top of your fraction. And then you're dividing it by 1 plus cos x. Now, this is just the left side. So it's important to note which side you're actually focusing on. So in this case, I'm saying left side equals this. And I'm not even touching the right side. So don't look at the right side until you kind of work with it. So I find the most troublesome stuff with proofs is the jumping. Don't jump. Stay on one side. Keep it consistent, okay? So now what we're going to do is get common denominators for the first fraction. So as you can see, there's a cos in your denominator for the first part. So I'm going to multiply this first part by cos x and the bottom by cos x to get common denominators. So that's going to give me sine x cos x plus sine x over cos x, right? So that's the first part, just as a common denominator. And then you're multiplying by the reciprocal, which is 1 over 1 plus cos x. Now, another thing that's a common step with proving is that if you have, you can factor, meaning if you see something in common, you can take it out. And that's going to be really important for the next question as well. If you see kind of common factors, factor them. So in this case, you'll see that the numerator, you can factor out a common sine x, leaving you with cos x plus 1 within the brackets over cos x multiplied by 1 plus cos x. And by doing that, I can cross off these factors of 1 plus cos x. Okay. So then what you should find is that you get sine x over cos x, and that's actually equal to tan x if you wanted to write it as a single trig function, right? So this would be your answer for the left side. Now, if you look at your right side, it doesn't look like that right now. So that is where we have to now switch to the right side to see what we can simplify it as and see if we can get them both to be either sine x over cos x or tan x, right? So let's look at the right side now. So this is where we have a double angle. Sine 2x is the equivalent of sine 2 sine x cos x. So that's using your formula sheet. And then 1 at the bottom, I'm just going to leave it as it is for now. If I'm looking at it, it makes more sense to leave it like this. The reason being is that the 2's can cross each other off, and the cos factor at the top can cross off with one of the cos factors at the bottom. So then what you're left with is at the top, just sine x over a single cos x, and that's equal to tan x. And then at the end, you always say, therefore, left side equals right side. And then you can even put like a little square shaded in, whatever you want to do. Okay, so once you see that both sides are equivalent, that's where you kind of say a therefore statement. So it's like your summary saying, I did it. So that's question number 3. If you want to verify this, you could put the left side into y1, the right side of the equation into y2, and you should see that they overlap. So if you have a newer version calculator, it's really helpful to see because you'll see like one color and then you'll see the other color go right on top of it. Okay, if you make an input error, then you're going to see that they're not going to overlap properly. So you just got to watch your brackets once if you put it into your calculator. Okay, so verifying is always key, is making sure, of course, we know this is going to be an identity because we just found that left side does equal right side, but it's just nice to kind of know there's certain questions where they say, is it an identity? Where, well, you can quickly check with your graphing calculator. So that's question 3, is looking for those kind of common things. Now, the other approach, the longer approach, is that you could have multiplied this left side by the conjugate, which is 1 minus cos x, the top and bottom. Then you distribute, but it ends up being like 15 steps versus here I only had to do like 4 steps on the left side and then 2 steps on the right side. So it didn't take long to get there versus 15 steps. Like I'm counting and it's time. It's like, wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 rows. Okay, so 11 rows of work versus here it's only 4 rows. So it does make a difference. It's picking one version versus the other. If it starts to get too long, you might want to revise because sometimes people get stuck, I find, with these kind of proofs. So that's question number 3. And then your last one, question number 4, they want us to algebraically solve for this. So this is where if you ever have any kind of double angles, replace them. If you ever have any kind of sign with cos, factor it. So if you look at this, there's actually 2 ways to approach this. We can write it as like a cos, like 2 plus 2x plus x, and then simplify it that way. But I'm going to use, for question number 4, I'm going to do some replacements and then get it to factor nicely. Okay, so this is what I would do. Is instead of cos 2x, I would rewrite it as this on your formula sheet is the equivalent of saying 1 minus 2 sine squared x. Now, there's multiple options that you can substitute. So that's kind of, again, the tricky part is figuring out which one will give you the least amount of steps. I don't know why this circle kind of appears. Okay, so this cos x stays the same. So all I did was I replaced this cos double x with that from my formula sheet. And then the double angle for sine, that one's the easiest because there's only one option. It's 2 sine x cos x multiplied by sine of x, and that's equal to 0. So what we're trying to do is simplify this as much as possible so that it's nicely factorable, and then we can easily see the solutions, because right now it's a mess. Okay. Once we have these parts in brackets, we're going to distribute and join them together. So we're going to have cos x multiplied by negative. So when we multiply that in, we get cos x and then minus 2 sine squared x cos x. So that's distribution there. Then we do the same thing here. This is just going to multiply to the sine squared x because it's just one factor multiplied by another. So it's minus 2 sine squared x and then cos x equals 0. Now, if you look at it, these guys are actually the same factors. Terms, they're the same terms. So these are like terms if you look at them, which means that we can add them together and just join their coefficients together. So that is something that can happen. So we have cos of x, and then we have negative 2, and negative 2 becomes negative 4 of these sine squared x cos x values, and that's equal to 0. Now, just like in the previous question, if you see something in common, factor it. So I see that they both have a cos x in common. So I'm going to factor it outside of the brackets, leaving me with 1 minus 4 sine squared x equaling 0. And this is where it's like perfect. This is what you want. You want each factor having its own trig ratio. You don't want to have a mix of ratios, which is what I was trying to eliminate from the start. So as you can see, this factor, if you look at it, could equal 0, and that could be easily solved. And then we have to look at where 1 minus 4 sine squared x could equal 0. So those are our two factors that we need to solve for algebraically. So for the first one, I like to look at those quadrantal angles, of course. Like this is, again, something I just know it in my brain that I just, well, don't know that. The positive one, I keep doing that. Okay. So I'm just writing out those quadrantal angles. The more often I write it, kind of like ingrained itself in my brain. So it doesn't take long, and I just find it's nice to kind of write these out and see it for each question. Okay, so we're looking at where the x coordinate is 0. Well, the x coordinate is 0 here and here. So that's going to occur, and this is kind of like the most common that they ask in questions, is when cos x equals 0 and when sine x equals 0. So cos x is always equal to 0 at pi over 2 and 3 pi over 2. Now, what you need to remember is that this simplifies to pi over 2 plus pi n, where n is an element of integers, right? So remember how pi just means 180. So to get from 90 to 270, I have to add pi. And if I want to keep going, you're always adding or subtracting pi's, okay? So that's the general solution to represent pi over 2, 3 pi over 2, and etc. And again, if they don't give you a domain, you need to kind of write the general solution, which is this. This is the general solution here. Now we're going to go to the other equation and look at where sine squared x, we have to solve for sine x. So we're going to bring the 1 over to the other side and divide by -4. So that's going to be sine squared x equals -1 divided by -4. And then we're going to square root that. Square root both sides. Now, this is where a lot of people forget that when you square root something, you have to put positive and negative to get the answer, right? And the reason that's important is you're going to miss out solutions if you don't include that positive negative when you square root the value, because that means that you can have an answer in quadrant 1, 2, 3, and 4. So for these, you can either look at the unit circle and say, where is the y coordinate equal to 1/2, and then see where that occurs, and then write out all the kind of all the answers. Or if you didn't want to memorize, or if you were in this course and you had that diploma and you didn't want to memorize the unit circle, you could always go back to degrees and do x equals sine inverse of 1/2. Now, the inverse of 1/2 in degrees is 60 degrees. Nope, 30 degrees, sorry. It's 30 degrees, which means that it's going to be pi over 6 in radians. So if you remember like those main ones where it's like pi over 3, what is it? Pi over 6, what is it? Pi over 2, 3 pi over 2. If you remember those, then it becomes really easy to kind of work with degrees and then quickly switch to radian. So once you know that the reference angle is pi over 6 for all of these, then all we have to say is that our general solution is going to be pi over 6 plus, to get from here to here, guys, you just have to add 90 degrees. And to get from here to here, add another 90 degrees. From here to here, add another 90 degrees. And from here to here, 90 degrees. So if you keep adding 90 degrees, you're going to get to the next answer. So that's why we would put plus pi over 2n. N is an element of integers. And this takes care of every solution that's possible. Okay, so yeah, if I take 30 degrees plus 90, that gives me the 120 degrees. And if I add another 90 degrees, that gives me the 210, right? So that's always going to give me that same reference angle around the circle, either going in the clockwise or counterclockwise direction. So this is kind of like the tricky part with these last two kind of sections is like writing the general solution and how to summarize it. Because usually you would just go this. Usually you would just add 2 pi n if it's something that doesn't occur every quadrant or every 2 quadrants. But if you can make it simpler and easier to look at, that's what we're trying to do here. Okay, so that is question number 4. And as you can see, there's a lot of answers here, right? So there is, well, there's 2 factors, and we had to find out the general solution for both. And that kind of takes care of any solution that's possible. So that's it for your trig. So if you guys get this done, then trig is over. So that's kind of like the most painful unit people find is this trig unit. And that's the one people struggle with the most. The next unit isn't, it's different. It's really, really different. So you're either going to like it or you're going to hate it. But it's a nice change, I find, is to end off with that. And it's really short. There's only 3 lessons with that last one. The big if? What do you mean big if? What's the if? If you finish this? If you get to it? What do you mean? Let me end the chat so we can, let me end the recording here. Why are you not going to finish?